Now we're a little bit more cozy. I'll try and keep my voice up, but let me know if it's fading. Okay, so you got up to this stage where you saw some of the basic traces, and hopefully Rich told you the promise of true online TD lambda, which is to try and get a really exact match with what you can do, let's say, after the fact. Okay, and so today we'll sort of get into the details of that. So to just remind you, I guess this is mountain car. This is a similar diagram to the ones that you saw last class. So this is a tabular 19-state random walk, and so the policy is fixed to this random walk on some chain, and this is a comparison of two algorithms, right? So on the left, you see true online TD lambda. So this is something that will just update time step by time step. And on the right, you see this offline lambda return algorithm, the thing which updates after you've seen the full trajectory. Okay, and then we're comparing the RMS error over a variety of step sizes for the two algorithms. And, well, what can we see? Which algorithm looks better? True online looks a little bit better. So why do you say that?
Because it has better parameter tolerance, it looks like.
Okay, better parameter tolerance. Is it ever lower at the lowest point? Kind of hard to tell, but just a very little bit, right? So it might be a little bit surprising that we can do this, but it's really getting us like the best that we can hope for, right? So in some sense, because it's updating at every single time step, it's able to use the most current information so as to update what will happen into the future, right? Whereas the offline thing is always updating with respect to things that are happening further off. Okay, so, oops, wrong computer. Let's see. These are the update equations for a true online TD lambda. So you'll see that it looks quite similar to your traditional TD, right? There we go. So we're updating our weights. So this is the old weights. These are the new weights. They get updated with alpha delta Z, where Z is our eligibility trace. Okay, but then it gets this additional component, which is like a correction factor. Okay, so it's a small correction factor, and it's needed to keep exactness. Okay. So you can see that really what's happening is you're comparing the weights just across two time steps with the feature vector. And so this term here will become very small. And then if we go and look at this other term, the Dutch trace, it will look similar to your standard accumulating traces, right? So you have a gamma lambda zt minus 1, but then it also has this correction factor. Okay, and this correction factor is what allows it to make an exact equivalence. And so these are sort of the different portions, right? So if you took out these portions in green, you would get your standard algorithm. You add in these correction factors, and you get to the new algorithm. Okay. So it's really quite similar to what you saw in the previous class. It's just a few extra terms, maybe a little bit of additional computation, but not that much. Okay, so the implementation is straightforward, right? You just add a few more characters into your code, and you're good. You have this. Understanding what it's doing will take a few more lines. Okay. So what's the theoretical basis for this? So that's where we're going to go. So this uses the truncated lambda returns for targets. So what do we mean by that? Well, we consider what would be the return one step into the future, or if we truncate the returns, let's say one step into the future, or two steps into the future, or up to n steps into the future, and we say, what would happen if we bootstrapped at that point? Then we can use that to update our values, and then we're going to do a lambda mixture of these. Okay, so let's first take a look at how we're defining this truncated lambda return. So G, we're using G's for returns. Lambda, this is just to indicate that this is a lambda return. And then we're considering a lambda return from time t to time h. Okay, and then we're going to consider an episode which is running up to time step capital T here, right? So t is sometime into the future, or some current time. Oops, no. Too many animations, Rich. Okay. So to sort of set this thing up, we're at time t. The episode will go until time capital T, and we're considering some intermediate time point h, so some horizon, which is between now and the end of the episode. And what do? We add up the lambda returns. We add up the lambda returns of the things that happen up to then. So 1 minus lambda plus the summation over lambda to the n minus 1. So n is our summation term, so we're considering each intermediate point. And we're considering the return from the standard truncated return from gt to gt plus n. And then at the end, we add on the remaining thing from that point on, which will be the return from from p to h. Okay, so as you might notice, there's more indices here than we typically have to deal with, but they're sort of necessary to get this exact equivalence. Okay, so we have this sort of standard picture where here's this character, this learner at time t, looking forward into the future, getting information from the future states. And, well, how is it updating its weights? There's going to be a weight update which corresponds to each horizon. Okay, so for each intermediate horizon between now and the end of the episode, we'll define a weight update for for each horizon and for each time point. So the weight with horizon h at time t plus 1 is given by the weight for that same horizon at the previous time step, plus a step size times an error term times the gradient of your current value function evaluated with the weights at h and t. Okay, and then this is the lambda return from t to h, right? So same h. You see that h hasn't changed in any of this equation, and on the right-hand side we only have time t. On the left-hand side we have time t plus 1, right? So using the information for every horizon, we update the weights. Okay, so we're going to have a whole slew of weights, at least in conceptual space. Yep.
Why do you need the h over the w?
Why do you need this? So if you think about what's happening in, well, we'll get to it, but if you think about what's happening in a Monte Carlo update, in the offline lambda return algorithm, offline Monte Carlo lambda return algorithm, what you do is you consider in retrospect how the weights would change at every single time step, right? And so there would be basically a quadratic number of updates because each of the weights is changing at each of the steps. And what this is doing is it's allowing us to speak as to what each of those updates, what the contribution of each of those updates is. Okay, and I think we'll see this on the next slide. Okay. So these are your initial weights with horizon 0, right? And this is with horizon 1 all the way with horizon t, right? And so that's the contribution that's coming from the initial weights as you sort of process through the sequence. These will be the contributions from time 1 to time t and on into the future, right? So in some sense, this will be very detailed bookkeeping, but the actual algorithm won't use it all, right? So we'll use all of this to define an equivalence, but then we'll only use the diagonal part. Okay? So what do we have? So the online lambda return algorithm says that for time point 1, what do? We update the weights with the lambda return up to time point 1, so from 0 to 1, minus a value function times the error, right? So if you just had one time step, that's all you would do. Then for time step 2, what do we have here? We go from, with horizon 2, we update W1, so T1, horizon 2, gets updated here. So where did, hold on, I always get messed up with these. We use W02 to get W21, and then we use W21 in the next equation. Okay. Where was W02 coming from? So yoink. Right, so W02 should just be the initial weights. There we go. Right? So what we do is we get sort of this whole lower triangle of weights, right? So a weight vector for each time point and horizon. And then we use one to compute the next, right? So this is what you would do if you were doing online lambda return algorithm. But you would do this, in some sense, after the fact. You could do it online. You could do it online, right? You could basically do this at each time step. Okay. Oh, sorry. So I guess we're not actually going, right. So maybe I went through this one too quickly. Yes.
Why do you need that?
So the thing that you care about is what's the net contribution at the end, right? And so really what you care about is getting the final weights. Like if you had I'm not explaining this well. Okay, let me come back to true online. I'll do Monte Carlo first, and then we'll see how it connects. Okay, so too many computers. Right. Okay. So we're not actually going into the details of true online beyond that. What we will go through in more detail is what happens if you wanted an equivalent algorithm for a Monte Carlo return, right? So it gets rid of a bunch of the additional details, but it shows how you can get the exact equivalence. And then actually showing the exact equivalence will require additional notation. So we'll stick with Monte Carlo. Okay. And in some sense, it's the simplest example of deriving a backward view from a forward view. So you saw a bit of this, right? But the versions that you saw up to this point would have been more approximate. Okay, so we're all familiar with Monte Carlo learning, right? You just have a target that you're trying to estimate. We'll derive these Dutch traces for the Monte Carlo setting, and they'll look the same as for TD. And it really shows that the Dutch traces and this exact equivalence has nothing to do with TD. It's about an efficient way to implement online algorithms, right? So instead of keeping around the full quadratic and doing additional computation, you can get it in like linear computation and linear memory. Okay. So what's the setting? We're trying to predict a final target G, right? So we can think of this in the TD case as being the return, but here it's just some target. And the target arrives at time capital T. Okay, and so when we start off, we have data, a feature vector x0. We have weights w0. The prediction of the final target at the first time step would be the dot product, right? W0 transpose x0. And it's always trying to approximate the final answer G, right? And well, until we get to this time step T, we have no information with which to update the weights here, right? So our weights here are W0, our weights at the next time step are W0, all the way up until time point T minus 1, where they're W0. Our predictions will just be the weights times the feature vector at each time point. Okay? So this looks hopefully familiar. And then we can do a weight update at time T plus 1, which is the old weight plus a step size times our error at this previous time point times the feature vector. Okay? Now, when can we actually do this update? We can only do it at time capital T, because that's when we get all of the information. Good? And then when we go on to the next episode after this, we'd start using W capital T, right? So the final weights. So here we see that the actual weight is only changing in between episodes. Good? So we're all good with the problem setting? Okay. So what do we want? There's many ways that we could try and make algorithms. But here's a set of properties that you might want. Right? So the computation per step to be constant, so it doesn't increase with the number of episodes. So things like doing a batch update over all of your experience are not constant. Right? Being proportionate. So proportional to the number of weights, or order n. This is perhaps a tricky one to get. Right? There's only some things which you can compute proportionately. And then the third one is really quite strongly related to things like eligibility traces and Dutch traces. So this idea of being independent of span. So if you don't want your computation to increase as your episodes grow or change in length, right? So then this is a special one, right? This is one that's sort of in a lot of the RL algorithms that we see here, but they're in some sense difficult to achieve in general. But if you think about biological organisms, maybe you'd say that this is a rather important one. And actually, if you start solving problems where effectively episodes get very large and you don't want to pause to process it, then you need something like independent of span. Okay, so this is to say that it's not increasing with the episode length. In general, the predictive span is the number of steps between the time that you make a prediction and you observe the outcome, right? So if you want to be able to make a prediction now and update in 5 years, and you don't want to have to do 5 years worth of processing when you get that answer, then you want something that's independent of the span. So you could update all the weights in between that you were using. Okay, and we see that, well, does this have this property? Well, if all the work is being done at time t, then maybe not. What's the span of this algorithm? How many time steps between t? And is Monte Carlo independent of span? No. Okay, because it's doing all of this computation at the end. Okay, and so because of that, the Monte Carlo algorithm is not independent of span. And so this is sort of what are the key attributes of what we're going to get. We're given an initial set of weights. There's going to be features that arrive along the way from time 0 to time t minus 1. We get a return of g. The Monte Carlo algorithm is to say, let's do this update for all t's. Okay? And so this is a vector of size n, span of size t. You have, let's say, oh, sorry, no, I think he uses d for a feature or dimension of the feature vector, but you know, you get something that's the size of the feature vector times t, right? Because you have to first do t to get t plus 1, then you use t plus 1 to get t plus 2, and so on. Okay. The independent of span algorithm, right, is given by this set of equations, or this set of updates. So what do we have? We basically have 3 things here. We have a way to define the final weights, the weights at the end. Wt is going to be some other vector a from the previous time step, plus g. G was our target that we saw at this time step, times our trace, z of t minus 1. Let's skip a for the moment. Z, what does that look like? Z is going to be the initial step size times x naught, so our initial feature vector. And then after that, it's going to be z at time t is defined to be z of t minus 1 plus alpha t x of t. Okay, so we can think of this kind of like a trace, and it'll have this additional term in between. Okay, so this is our trace, and this is basically, well, it's a helper vector, right? It'll store an intermediate results. I think they call them provisional weights. Okay, so let's look at this. Does this set of equations satisfy our desired properties? Is it independent of span? Is the amount of computation that we do per time step bounded by a constant? Yes. Okay. What were our other desirables? Let's go take a look. sorry, what were they? Constant. So doesn't change with the number of episodes, right? It's independent of span. Because it's the same computation that you're running basically on every time step. I guess there's that one additional thing, but.
So here you've just shown setting W uppercase T.
Yep.
But so then how do you get W for the other time steps? Are you saying you could subscript those with little t's and you get G of little t, or?
Well, so we only actually care here. So in this Monte Carlo setting, we only care to do the update at the end.
Okay.
Right, but previously to get the update at the end, we would have to compute all of these intermediate weights.
Yep.
Here, perhaps it's notational for notational clarity, but the weight updates are effectively being stored in A or something akin to them, and then it's just getting copied into the thing when the target G arrives. Okay, so the last of our three is computation. Is it proportionate? Is this a linear computation? Is it quadratic? Is it cubic? What does it look like? So these terms are vectors, right? Let's start with this. So x is a vector, alpha is a scalar, so z is a vector. W is a vector, right? Let's start with our trace equation. Well, that's a vector times a scalar, so that's linear. That's linear. What about this term? Depends on how we merge the brackets, right? If we wanted to waste time, we could do the outer product of those two vectors, right, and do a matrix thing. But typically, if you have the opportunity, you would just do the dot product, right? So dot product would make that thing a scalar times a vector, and you're good. And there's exactly the same form here, right? So it's going to be linear. Good. And excusing the notation a bit, what we're going to see in the next few slides is that starting with the Monte Carlo algorithm, the W's that come from the Monte Carlo algorithm would give us a W capital T, and then this algorithm gives us another W capital T, and that they will be identical.
Because for the independence of span everything, you don't have to compute the weights for each time step, but you still have to compute A and Z. So what
Yep.
exactly is the independence of the span?
So it's the amount of computation per time step is independent of span, right? So here, the reason why this is not independent of span is that all the computation is happening at the end, right? So if you had to wait 5 years for the answer, then you would have to go back over 5 years worth of data so as to update every single prediction you made along the way. This one's doing the updates along the way and is guaranteed to give you exactly the same final output, right? Other questions? Now's a good point for questions, because next up is formulas.
Shouldn't perform better than non-Monte Carlo because you can use the updated weights already during the episode?
So this is only,
Just not use that.
right, so this is just doing the Monte Carlo version, as opposed to, sorry, this is, let's say, true Monte Carlo, as opposed to the true online TD. And so because we only get one target at the end, there's no updates to the actual weights until the end. In the true online TD, it's able to use the information along the way, and so it can do just a little bit better. Good? So what we're going to do is we're going to take this Monte Carlo algorithm and do a whole bunch of rewrites and get something that looks like this. Okay. Good. Ready? let the formulas begin. So we'll do this slowly. So it really is just methodically going through the steps. And hopefully we can get through them together. So what do we start off with? We start off with the Monte Carlo formula, right? So the weights for time t plus 1 are equal to the weights at the time t plus alpha times an error term times the feature vector, right? Alpha delta x. Good. And this is holds for all time steps between 0 and t minus 1. Okay. So now what we do is say, well, let's start with the very last update. Okay. And what do we have? We have the very last update, W capital T, is equal to the weights at the previous time step plus alpha times this error term times x at t minus 1. Okay. So I didn't have time to restore the fancy animations, but just pay attention to this first line, right? This first line is just the original formula instantiated for capital T minus 1. Good? And interrupt me if you have questions. Good. So that's what's the next step? The next step is just expanding this thing out, right? So we carry this term down. We have an alpha g xt minus 1. We pull that term off to the right. And we have a minus wt x of t. And what do we have here? This is a scalar term, right? Transpose times the vector. And so we pull the vector out here. We have the scalar term. No. Sorry. Too many animations. I'll just point up to the board at this point. Hopefully that's less error prone. No, probably not. But we have the second line. The second line is just rewriting the terms. What's the third line? The third line is saying, now we want to pull out this wt minus 1. We have a wt minus 1 over here. We have a wt minus 1 over here. So if we just put an identity matrix in front of the first w, we can pull that out. And then we pull out this minus x of t over here. So we have minus alpha xt minus 1, xt minus 1 transpose. Good? And now let's just define f of t to be I minus alpha xt transpose. Okay? And then we can replace this term in brackets, or in parentheses, with an f of t minus 1. Okay? And this is called the forgetting or fading matrix. Why? Okay. Why? That's a good question. Can you answer it? Okay. So this is going to end up being kind of like a trace. Let's see. What are we doing here? So we're taking the identity matrix and removing the feature vector times the feature vector transpose, step size of it. Rich told me why he called it that, but I forgot. So I'm forgetting. But I expect it makes a lot more sense in the eligibility trace version for TD.
Yeah, isn't it just if you have positive features, then the FT is going to have entries that are smaller than 1, and you're multiplying it by your past weights to get you new weights, so you're kind of forgetting parts of the weights from the last iteration.
It could be. Yeah. It's not forgetting very much, though, right? Because this is just one step. But if this was, let's say, what's a canonical case where, yeah, not really sure what this outer product would look like in general. It might have many negative terms. Sorry, like even if the feature vector is positive, right, the outer product of these things might have, you might just be removing a little bit on something on the diagonal. You might not be. Might be good to work that out. Let's see. X of t transpose. Sorry, I have to use my hands. Not particularly good with these guys anymore. Yeah, I think you might remove a component on the diagonal. So it would be removing it just a little bit. But it's worth trying out. Other questions? Okay. So we have a matrix times a vector plus alpha target times a vector. We've defined this forgetting term. And now what we're going to do is we're going to recurse. Right? So with this general definition of f, we've used it at just the very last time point. And we've defined W capital T. We've shown how that goes to Wt minus 1. Sorry, how Wt defines the formula for Wt minus 1. But in fact, this holds for arbitrary t. And so what we can do is substitute t minus 1 for t. And that would allow us to get this formula, right? So if we take all of this and put it in for Wt minus 1, we get that component there. Clear? Clear-ish? Good. So next step. I don't know how Rich uses this. Okay. So we have f of t minus 1, just expanding out, f of t minus 2, Wt minus 2, plus alpha g, f of t minus 1, xt minus 2, xt. So what have we done? We've basically pulled out the alpha g terms on the right. We've pulled out a product of f of t's on the left with a Wt minus 2. And now we just keep doing this, right? So at each step, well, we'll probably do it at least once more. So let's replace the Wt minus 2 using this formula for general t. So basically plugging in that top equation, we now have f of t minus 3, Wt minus 3 plus alpha g x of t minus 3 plus an alpha g term. Splitting it out again, we get, again, a product of f of t's, Wt minus 3 plus alpha g, and the terms associated with alpha g. Okay, and if you do this all the way down to the very first time step, what do you get? You get a full product of f's until you get to W0. We can't go past W0. That's where we start. Plus alpha g times the summation of these f matrices times the x. Right? So we've now basically rewritten the full set of computations that go on in this Monte Carlo update. And now what do? We define at minus 1 to be the product of f times the W0. So this is what happens to the initial weights as it goes through time. And this is the contribution from each of the feature vectors that we see along the way. Okay? And we put that into a term called zt minus 1. So that looks kind of like a trace. Then we can write a of t minus 1 plus ag zt minus 1. Okay? And the short-term memory vector is a of t. are vectors. Z of t is another vector. Good? So we have a whole collection of definitions now. We've rewritten it. Now let's see if we can make an effective algorithm. So another collection of formulas. Where are we? And why do we need these formulas? Well, we don't want to actually do all those matrix computations, right? We don't want to do the products of f's because that's expensive. We want to be linear. Okay, so if we look at z of t, we can see that it's a product of these f's. And what we're going to do is we're going to see if we can write this in a recursive form that's computationally efficient. So taking the right-hand side there for zt minus 1, we basically make a mirror of it, or a general form of it, with z of little t. So we define z of little t to be the sum from little t to k plus 1, where k goes from 0 to t. Okay, so what's this doing? So it's f of t minus 1, f of t minus 2, all the way down to f of k plus 1, but this is actually a decreasing sequence, right? So the very first term of this sequence for, let's say, x of t, right? So if we consider k equals t, this is trying to go from t down to t plus 1, and that's a vacuous sum, right? You can't go from, like, these are supposed to be decreasing numbers, so t minus 1, you can't end up at t plus 1. And so the very first term is really just a vacuous product, so it's just the identity. Okay, so we have an x of t here, and we have from a sum that goes from t to k plus 1 of x of k, where we've dropped the index down to t minus 1. Good? So we just pulled off the term corresponding to t at the end. Then what do? Well, all the remaining terms will have this f of t in it. All right? And so we can pull out this f of t and consider the product of the rest. And then what do? Well, we notice that this term here is equivalent to this with a shift in index to being 1 smaller. Right? So we say that's all equal to f of t times zt minus 1 plus x of t. Good. Let's pause here for a sec. This is looking good. We've got z in a somewhat recursive form, right? Still a matrix there. Now all we really need to do is perhaps get rid of that matrix. Okay, so are we good up to here? Any questions up to here? Good. So now we expand f, right? Remember, f, this fading or forgetting matrix, was the identity minus alpha and the outer product of x. Okay, now z of t minus 1. We just do the expansion, so identity times zt minus 1 is zt minus 1 minus alpha, this term, zt minus 1. Okay, that's straightforward. Yeah, just expanding through. Next step, we're regrouping. Why can we regroup like this? How are we able to change this order? So right here, we went from this line to this line. Well, yeah, this is just a dot product, right? And we can write our dot products either way. And so here we're just writing the dot product the other way. right? Okay. So writing the dot product the other way, we now have 2x of t's on the right-hand side, so we can group. And what happens when we group? We get a 1 times the x of t, and then this is a scalar, so that's why we're using 1 instead of an identity. Alpha zt minus 1, dot producted with x of t. And so now what we have is a formula for z, which does not involve any matrices. Good? That's good. So z is now clear of these f's. And A still has this product of f's, but this one requires a little bit less effort. Because why? Well, we've defined, well, I guess akin to this, right? What we do is we define A of t for arbitrary t instead of just the last time point. And it's going to be the product from f of t down to 0 times w0. And it's easier here to see, it's from this formula, it's quite easy to see that it has this recursive form, which is f of t times at minus 1. And then if we do the expansion again, we get this is equal to at minus 1 minus alpha x transpose at minus 1. And, well, this is nice because A is a vector, and it's defined as a vector minus, that's a scalar right there, so minus another vector.
Why don't we just stay at the third, like the last, the line where the same product is in the
Sorry, which?
A? This line?
The-
Line or not?
This line.
Because this line would be using the same calculation that we already did for A. Or are we still going further with changing the equations?
For A.
Yeah, because for this we need alpha xt transpose, and for A we also need alpha xt transpose.
But the thing is, we never want to compute xt transpose, right? Because that will give us a matrix.
We need to compute it anyways for A.
Oh, yeah, so sorry, we don't. Because what we do is we group this, right? So we take the x transpose to at minus 1, and that's a dot product, right? So the ideal of avoiding matrices is basically enforced through these algorithms, right? If you wanted to use matrices,
You're gonna get slow.
well, you are slower, but your algorithms might be easier to define, right? Might be. So, but it is nice when we can reduce everything to linear time, because it ends up mattering. Other questions? Good. So now we have everything in terms of vectors, and let's see where we are. Yeah, we just started with Monte Carlo, and we defined these update equations, right? We basically rearranged until we got these, and this gives us the equivalent independent of span algorithm to the original Monte Carlo algorithm. Good. Let me see. So let's see what this actually shows, and then I'll have to go back to do it. So we've defined Dutch eligibility traces from a Monte Carlo update without any TD learning, right? So there was no TD in what we just did, but there's these Dutch eligibility traces here. Well, is there? So let's try and keep this in mind. Let's see this guy, maybe. So we have an alpha xt and axxz. Let's go back to where we defined our Dutch traces. I'm hoping it's here. Okay, so let's see, Monte Carlo. So let's ignore these terms. So we have z gets z plus, we add on an x, and we have z transpose x times x. And let's ignore those terms. So let's see, we've got an alpha z transpose xx. And let's see if we actually have that. So ZZ, and there was an X term. The other term was what? ZXX, but I'm assuming that's equivalent to this. Let's see. We would take X transpose times Z, right? So eligibility trace times the feature vector. And this, let's just check it once more, should be what we have over here, right? So maybe there's been a transpose involved, but it's really the same terms. Okay.
Why isn't alpha on the upside of that?
Why don't we have an alpha on the X?
Yeah.
We don't
This
have
is-
it there as well. I think there's a mistake.
Sorry?
I think we don't have alpha on the X in the next slide. I mean, not at least not in the book.
Oh. Are the formulas on these slides not equivalent to the ones in the book?
Yeah, can you show the one we derived from Monte Carlo?
Right?
So here, it's not on the X.
Right, but there is, yeah, an alpha in the next drop.
Is this alpha not in the one that we had in our derivation? Sorry.
Derivation, but not in-
It's not in the book.
There's no plus x.
Hold on. Alpha da da da.
There's no alpha.
Let's see if we can get to the bottom of this one. Ah, so there is no alpha here, right?
No alpha, so the mistake is only in the next slide.
Okay. Yeah. Rich, I think, was editing these slides last night. Alpha t is the step size for time t. So this is written for a variable step size, right? And actually, Yeah, maybe there's a couple of comments here. One is that there's several different ways to write these algorithms, and depending on which paper you read, they've rewritten the terms in slightly different ways. So that's one thing to be aware of. The book is hopefully consistent. If you notice any inconsistencies in the book, please let us know, or please let Rich know. And then, yeah, I think this doesn't equal the derivation, at least not to my eyes. So right. So what's A0? A0 is W0. And it gets that term. Z gets ZT minus 1 plus, yeah. Right, there we go. That's, the X should be loose. Or the X term should not have an alpha on it. Good. So, typos and proofs. If you do the derivations, you can find the errors, but it requires quite some care to get it right, and this should get corrected. Okay. Other questions, other errors? Okay. So, this is the big piece of what I wanted to cover today, and then there's basically a few small additions. Okay, so this shows Dutch eligibility traces from Monte Carlo update without any TD learning. There's, if we go back to the true TD, those equations are basically analogous to these Monte Carlo ones. The derivations are just a bit more involved. The whole point of Dutch traces as opposed to accumulating traces, it's not really about TD at all. It's just about efficient multi-step learning, right? So how do you make something independent of span? And this is a slightly special thing or novel thing in the sense that it's taking some basically non-obvious algorithms in some sense, where you take some algorithm that has properties that you like and you make something that's algorithmically equivalent to it, but one that has better computational properties. Okay? And so this is a different type of machine learning result than ones that you'll have seen before, because this is an algorithm equivalence, right? It's not saying that this is a better algorithm really, or that it'll get a different result. It's just getting the same result in a computationally more efficient way. Okay? And this is an example of how you go from a forward view, which is, let's say, the Monte Carlo thing that we started off with, to a backward view, which is this efficient way of updating your weights. Good? Okay. So what happens when we take this and try and do something in control? Well, you saw basically Dutch traces on Monte Carlo. We gave you the formulas for true online TD lambda. And if you take TD lambda and you do action values instead of state values, and you use it for control, then you would get SARSA, right? It's just putting action values everywhere where you would otherwise have state values. And then you can run it on Mountain Car and see how it does. So this is Mountain Car with 8 tilings with evaluated over a range of step sizes, alpha. Okay. And let's see, what are we measuring on the left-hand side? It's the reward per episode averaged over the first 20 episodes and the first 100 runs, right? So this is really the early part of learning, right? And what do we see? Well, so if we used Sarsa Lambda with accumulating traces, actually, how many of you guys have run Mountain Car? Have you done any programming assignments? Not Mountain Car? Okay, so Mountain Car is this problem where, you know, the car is sort of sitting in the bottom of a valley and it's got to sort of pump back and forth until it eventually gets to the top of a hill. And so it can spend a lot of time just sort of wiggling around at the bottom in the valley. And so the first few episodes are not particular, like there's many time steps in which the car doesn't really know what to do, right? And you can have really long time steps. And if you just use regular accumulating traces, the features that are associated with being at the bottom of the valley, you'd encounter those a lot, right? And so this would make your traces get large, which means that if you have a high step size, it would diverge, right? So Sarsa Lambda with accumulating traces only will work at all if you have relatively small step sizes. Okay? And it does reasonably well, right? It gets -1 per step, gets to maybe 250 or so, maybe a bit lower. But it's not particularly robust, and it doesn't do the best on this chart. So you've also seen replacing traces in the last lecture. Replacing traces, I think. So they're starting to become a bit deprecated now because we have better things, right? And the situations where they're properly applied are somewhat limited. But you can apply Sarsa Lambda with replacing traces, clearing the traces of the other actions. And you can see that it's robust across a larger range of step sizes, right? It learns to solve the task, gets a reasonable reward, but it achieves lower performance than these newer algorithms. Well, so this is Sarsa Lambda with replacing traces, and let's say blue is a variant. Red would be the more common version, let's say, where let's ignore the discussion of replacing traces, but there's a variety of things that people do to try and make them work. But we see that both replacing traces and accumulating traces here work visibly worse than true online Sarsa Lambda, right? And this is true across a range of problems that it's more robust and you're getting better performance. It's squeezing that last bit of performance out, and it's also robust to, let's say, the traces don't get too large, or you can avoid it.
Can you go over the update for the trace for the accumulating versus replacing?
Okay. Do we have it on here? Let's see. Did you see it on the slides last class? If not, we can. Okay, so let's look at what the accumulating trace does. Let's just pretend that this is the feature vector x. Okay, so what the accumulating trace does is it says, let me take the last trace, decay it by the product of lambda and gamma. Lambda and gamma are both less than 1, right? So, or at most 1, right? So this will, z of t will never be larger. So, sorry, zt minus 1 here would never be larger than zt, just if you had that term. And then we add on the feature vector, right? So accumulating traces says, take my last trace, take my last eligibility trace, decay it by a little bit, and then add on my new feature vector. Right? So if lambda was 0, it would decay completely, right? And you'd be back to something like, you'd be back to TD0. If you set lambda to be 1, then it would just take the full trace, right? Decayed by gamma, and then adds on the new feature vector. So if we took the other endpoint from lambda of 0, if we took lambda of 1 in an episodic task where gamma was also 1, then it's really just adding up the feature vectors, all the feature vectors that you encounter, and so it would become very large, right? And this is what's happening in that mountain car example. The accumulating trace is becoming very large as the norm of that vector. Replacing traces, what that does is it says, I will do this decay, but instead of adding on the feature vector, it assumes that any non-zero element in here replaces the component in the trace. So replacing traces is really designed for binary feature vectors, so zeros or ones. And so it says it's going to remember when this thing was last active based on the product of lambdas and gammas. Okay? But it's really restricted to that binary feature vector case where it makes sense. And I think he has a picture of it here. So if we look at how do these traces behave over time, if this was your feature vector, and let's say that this was, let's say, a binary feature vector, right? So you have 0 and then a 1, 0 and then a 1, 0 and then a 1, 0, 1, 1, 1, 0. What happens to your accumulating trace? It goes 0, it adds on the 1, decays a bit, then adds on that 1, decays, adds on that 1, decays, adds a 1, decays a little bit, adds a 1, decays a little bit, adds a 1, decays a little bit, adds 1, then decays again. Dutch traces really prevent the trace from going up too large. So it goes up a little bit, decays, up 1, decays. Oh, sorry, it doesn't go up by 1. It goes up by less than 1. Right? So you can see that the peaks are lower. It goes up by, like when it's at 0, it'll go up nearly a full amount. But like here, it only goes up just to, like it doesn't even go up twice as high. Right? Replacing traces starts at 0, goes up, goes down, but then it goes to a max of 1. Right? So you're really replacing that element of the trace with whatever the feature vector is. Okay, so this is really well behaved. It's bounded. Right? You can bound the norm of the eligibility trace, which means that you can pick an appropriate step size, like a priori. Dutch traces are, you know, not quite as well constrained, but they are well behaved and they provide this exact equivalence that also, or yeah, they provide faster learning and they're better behaved, right? They're not as well behaved as replacing traces, but replacing traces don't make sense in general. They're much better behaved than accumulating traces. Other questions on this? Okay. This, more animations. Good. So bringing us back to here, if we consider applying these various traces to conventional control problems, we get to the perspective that True Online is doing a better job on conventional control problems. Good. Clear? So we've done TD lambda. We say, well, what if we just replace those state values with action values, make a control algorithm out of it, and we're here, right? We get to better control performance. And stable over a range of step sizes. So the next few bits are other variants on what we can do in control with using action values. Okay, so we've seen control, we've seen SARSA, right? We've seen Q-learning, right? We've seen n-step backups and such. And so there's a natural question, do we have eligibility traces for Q-learning? And the original version is, or one of the original versions is Watkins Q lambda. So what does Watkins Q lambda do? Just for expressing this with the standard backup diagrams, is it says, take all of the backups weighted by lambda up until the point that you take a non-greedy action, right? So this is really designed for epsilon greedy style algorithms. So when you're greedy, you would just do standard backups. You would allow your trace to continue growing. And then the moment you do a non-greedy action, you would do a max over all possibilities. Okay? So this is one way that you could do or get to traces with Q-learning. There's still, let's say, some issues with it. A potentially better thing to do is to do a tree backup. So actually, before I show this, let's go back to this one. These backup diagrams are familiar, okay? And you understand what they're intending to express, right? So you take the weighted sum of these trajectories, right? And at least that's the way that you can understand them. So the tree backup, well, maybe you've seen this. Here what we're doing is we're considering trajectories of various lengths, right? Up until the end of the episode. We're again weighting by lambda, but here it's considering all possible actions at the bottom, or at each stage along the way. Okay? And so here, well, maybe this behaves a little bit more like SARSA, or expected SARSA, right? So there's no maxes in this backup. But we can define like straightforward, simple backup rules, or an algorithm. Right? So what do we have here? We have a trace which depends again on the gamma and the lambda, but it also depends on the probability that this action was taken by the target policy pi times the old trace z of t, plus what you could imagine would be your feature vector. Okay, and then the update would be the standard update equation. Now, one nice benefit of this is that there's no importance sampling. And why is that a benefit? Well, importance sampling can blow up. And it's often difficult to try and control what importance sampling is doing. This can behave relatively well, sort of like SARSA, but despite that, there's still no theoretical guarantees of stability when used off policy, right? So good. So this gives you another update rule that you can use instead of SARSA when you want to use traces for control. Good? Yep. Why is there no importance sampling? Because they wanted to avoid it. Right? So when does this make sense? So this is basically following the policy, right? So this again is only going to be really useful for control if you're behaving in a nearly greedy fashion, because it's updating based on what all the possible consequences are, right? There's no maxing here. So if the behavior policy isn't greedy, this thing's not going to learn a very good control policy. Or if the behavior policy isn't close to greedy, it's not going to learn a good control policy.
And if max still the reasons important sampling,
Sorry?
so if there is a max, I hear the average and it's more important sampling. It's
Right.
fine. But if we have a max, like in Q learning, we still don't have important sampling.
Right. So you could do something like this, right? So what's Watkins Q lambda doing? It's saying, let's just take the direct traces every time step that we're acting greedily, and let's take the max when we don't act greedily, right? But what happens if we're far from greedy is that our traces will be really short. Or like, we'll always be cutting off our traces. I guess that's not really shown here, but basically the moment you take a non-greedy action, your eligibility trace is going to be set to 0. And so you're not going to be able to update states that are far back in time, right? The moment you take a non-greedy action, you say, I can't say what happens to things in the past. So this will also only give let's say, temporally extended updates, right? It's only going to update states that you visited far in the past if you've been greedy all the way back to then. Good? Okay. So the final one is to try and introduce importance sampling. Okay, and I'm just going to put a little bit of it up because it gets complicated, and yeah, it would require us to do way more formulas than I had time to prepare for. So, off-policy traces with importance sampling. So I mentioned that the other algorithms, SARSA lambda or Watkins Q lambda or tree backups, were effective for control when you were behaving really close to greedy or really close to a good policy. And even learning about another policy, that's the places where they would be particularly well suited, right? So if you were just using it for prediction, they'd be well suited in the situation where the behavior policy and the target policy were really quite close. You might be in the situation where the behavior policy and the target policy can be quite far separated, right? And in general, it's really hard to learn about that, right? So it's really hard to learn about, I don't know, snow if you live by the equator, maybe. I don't know. That's not really policies, but it's hard to learn about walking if all you do is swim, right? And if you're only walking for a portion of the time, then you'd only really learn about walking from that portion of the time. Maybe you're walking under the water, and that's a little bit different. But there's a sort of ideal that you could learn about one policy, one way of behaving, when the way that you actually behave isn't exactly like that, right? And that's what we have with epsilon greedy. It might be what you have when you operate under a softmax policy. It might also be what you get when you're learning from logs of data or such, right? And the main tool in the toolbox for learning in this setting is to use some form of importance sampling, where you try and compare the behavior policy. So what's the probability that you would take this action from this state? Like, what's the probability that this style of transition is encountered in the actual data? So that's your behavior. Versus what's the probability that this style of transition would be encountered under the target policy, right? And this gives you a ratio. Okay. Have you guys covered importance sampling before? Okay, good. So then I don't have to give the rest of that. But remember that it's really this row term that captures your importance sampling, right? And guess what are the other important bits to remember about importance sampling? Your behavior should cover everything, right? So you need to have coverage over a set of all possibilities. And what should rho be an expectation in the long term? Huh. Yeah, 1. And it's worth thinking about that. So that means sometimes it's got to be lower than 1 and sometimes higher than 1, right? So if the behavior has a low probability of doing something and the target has a high probability of doing it, your rho is going to be perhaps much larger than 1. And if you do this for several steps in a row or in a sequence and your rows are multiplying together in some way, then you can get really large importance sampling ratios. So that's one of the ways that importance sampling tends to increase the variance. Okay, but given a row, we can define state-based returns and a conventional forward view update. So what does this look like? I'm just putting down the formulas here. So we have rho times, well, this term. What does that term look like? There's a reward plus gamma times 1 minus lambda v. So this is our state estimate, and this would be the future. Okay, so this is looking like if things are good, and this is, well, if rho is 0, what does rho 0 mean? Maybe we'll start from the other side. Rho 0 means that the target policy wouldn't ever do this thing that we're doing, right? So we would say, if the target policy wouldn't do this, then we say we're just going to trust the existing value function, right? So 1 minus 0 is 1. So we'll just use the old value. And we put no weight to the experience that we just saw in this transition. Whereas if rho is, let's say that rho is 1, then we would ignore this value, and the forward view would be entirely defining the return as being something akin to just a pure forward view, standard forward view. Right? So a lambda discount on the value plus the return. And with this forward view return, we can say this is what my preferred weight update would be, right? I would update my weights, or let's say that I was waiting until I actually had the returns to do this. Then I would update my weights based on alpha times the return minus the current value times the gradient of the value. Okay? So this is defining the lambda return with an importance sampling. This is using it in a forward view, which is defining what the ideal target would be. But to actually use this in an algorithm that's fully incremental and online, after some work, which is sort of detailed in section 12.9, we get a more conventional eligibility trace update that includes a row term in front of gamma lambda z plus the gradient of v, and then an update to the weights, which is alpha delta z. Okay? So just looking at this, what do we see? Well, we can see that the row term is over here on the left-hand side. So this gamma times lambda times z, that's decreasing the trace, right? But this road term can either send this trace down to 0, or the trace time plus the additional feature vector. You can either send it down to 0, or can multiply it by a factor which is larger than 1. Right? So if you're trying to learn about something that's rare, let's say that it's 10 times more likely that the target policy will do something than your behavior, you've just blown up your trace by a factor of 10, and you've done it on a single time step. And if you do it again on the next time step, you've blown it up by another factor of 10. Right? So, okay, you can sort of prove that when things are well behaved, this will converge to the right place, but for the things to be well behaved, like, you have to make sure that your traces don't get too large, right? And so there's this sort of bit of a fight between getting the theoretically ideal thing and getting something that's stable in practice, right? But even the theoretical guarantees are somewhat more limited here. We don't have theoretical stability under strong function approximation. In practice, it really depends on the importance sampling ratios as to whether this will be stable in practice. So if the behavior and target are sort of close, your importance sampling ratios will be well behaved. And you can go further, let's say, further from greedy, right, and still learn effective things here. But you can't ignore this variance that's coming from importance sampling, right? If you try and learn about things that are really far off from what your behavior would do, chances are you're going to get too much variance, and either your step sizes will have to be so slow that no learning is happening, or things will blow up, right? But if you pick your parameters appropriately, it can still work in practice. Good. All right, so we didn't do the derivation of how you would go from here to here. It's a little bit more formula manipulation. And the other thing that we haven't discussed here is there is actually a set of algorithms which are giving theoretical stability with some importance sampling. But when you use them in practice, you still have to be concerned with how much these variances blow things up, right? And so they're not things that you can, let's say, naively use and trust that it'll just work, right? You have to really pay attention to what's going on. Good. Any questions on this? Okay. So let's just wrap. So what have you seen perhaps over today and yesterday? We have an efficient incremental ways to combine Monte Carlo and TD, right? We have a full set of these eligibility trace methods, and we can get the advantages of Monte Carlo. We can get the advantages of TD, right? We have a proposal for a new and best algorithm. So let's say the thing that you would use by default is a true online TD lambda. And it has this exact equivalence to an online lambda return. And this leads directly to a true online Sarsa lambda. We saw three kinds of traces in sort of the conventional sense: accumulating, Dutch, and replacing. And in some sense, replacing is being thrown out. But there's certain situations where you might still want it, but by default, you'd go with one of these two, and perhaps the preference is Dutch. You saw traces for prediction and on-policy control. Then today we went more into detail and to traces for off-policy control and prediction. Hopefully you saw in some of the graphs yesterday that trace methods are better in various ways than n-step methods. And it doesn't come entirely for free, but it's still linear, right? So they have a small additional computational cost because you're storing around these extra vectors. But everything's still linear, small additional factor. Good. That's all I have. Do you have additional questions?
What happens if you arbitrarily cap the sampling ratios? Would that help? So let's
or 10, right? So this is a good way to keep things under control, but it will also introduce some bias, right? And so then there's this other game people play, which is how much bias do you want to accept in practice, and what's the consequence for your learning algorithm, right? Others? If not, that's everything. Thanks.